Okay, so last time we just tried to understand the relation between various representations of these canonical commutative relations. And so this is still of part 3, which is quantum field theory. And we'll finish this today, and then we'll go to inflation last lecture and put together everything we have learned about the background dynamics, about the perturbations and the quantum field theory, and see how one makes contact between observations and theory. Okay, so that will be next time, but today we'll just finish this thing. And so we saw last time that if you give ourselves some basis vectors, ek of eta, so this is the basis which is normalized. Then we've got a Fock representation. And that is to say we can write down our field operator phi of x eta as E naught k times e to the I k dot x times eta okay, plus the Hermitian conjugate. And then we define our Fock vacuum by just, it's annihilated by all annihilation operators. I'm not putting hats on the annihilation operators just to simplify the writing. So this is equal to 0 for all k. And that then gives us the Fock representation. So this is the Fock representation associated with this basis that we got up here. So the field operator is expanded in terms of this basis, and we saw last time that, however, we could use another basis, and we saw that any other basis, which we put at E bar of k, is really linear combination of these basis vectors. The reason is because Ek satisfies second order differential equations, so the space of solution is just two-dimensional, and Ek and Ek star are both satisfy that equation, and therefore we obtain this too. Therefore, any other basis will be with relative to Ek as alpha k, which has its constants, times Ek of eta plus eta k, where alpha beta are time independent. That is constants because both bases satisfy the differential equation, as we saw last time. So that's just constants, but they depend on k. That's the point up here. So for each wave number, we get this thing. So this is where we were. And now so then again, we can write down here, let me write as phi hat under bar of x eta. This is the concrete representation on the Fock space, let me call it F bar, determined by this basis vector E bar. Just as this is a concrete representation of the field operator on the Fock space, let's call it F, determined by this basis vector. So we've got some bases up here, and then the concrete operator is exactly going to look at the same form, E naught summation over k, E to the I k dot x, times Ek of eta times Ek plus Ek star of eta. So it is exactly the same form, but these are different basis vectors, and therefore these Ak and A dagger k are also linear combinations. So A under bar k, A under bar k dagger are linear combinations of Ak and A dagger k, just as E bar k. These are linear combinations of Ek and E star k up here. So that's what's happening.
There shouldn't be bars when you take product alpha and for ease on the right hand side of the.
Oh, they should not be bars, exactly. Thank you. Right. So they should be bar, E bar k just equal to that, and then here we just have this. Thank you. So basically, the field algebra is the same, right? And we're just representing it as concrete operators on two different vector spaces. And so The question that we want to ask is the following. Are these representations equivalent? And mathematically that means, are they unitarily equivalent? That is to say, does there exist a mapping U, unitary operator, from the first, from F to F bar, such that this operator is mapped to this operator. So you start with any state psi in F. In this Hilbert space up here, the first Hilbert space, you start with any state up here. And we can do two things. We can start with this psi and operate it by the field operator phi hat. X and eta up here, we can operate by the phi hat operator. And then go to a bar by the unitary operator. I just take psi, operate by this operator, and then go to, and then this element, this object up here is now an element of the F under bar Hilbert space, because I just have operating this U mapping up here. Or I can first take this psi and then operate it by U. So I first go to F bar and operate here by phi hat bar. So this object is already in F bar. So I can operate on it by phi hat bar. And of course then the total thing is again in F bar. And so I can do these two operations, and the statement is it is unitary equivalent if the two are the same. That is to say, I take an element psi, any element psi in the Fock space, operate by the field operator, and then go to the bar Hilbert space by this unitary mapping. Or I can first go to the unitary mapping, and I can go to the bar Hilbert space to do the unitary mapping, and then operate by the representation of the phi operator in the bar Hilbert space of the equivalent. So this is a statement of unitarity, and you can just see here this is true for all psi. So therefore, U phi hat should be equal to phi hat U. So that is to say, so this just says that it is the same as U. This is something that you have seen probably many times. So that I can just bring this U phi hat U minus 1 should be equal to phi bar. So that's the question that we're asking. Does there exist a mapping U such that this is true? This operator is in the bar Hilbert space, and this operator at the end is also in the bar Hilbert space. So that's the question that we're asking. And if this is the case, then we say that the representations are unitarily equivalent, and in that case, there is no. In other words, you can do calculations. Once you understand the meaning of each physical meaning of states, you can do the calculation either one representation or the others. And that is the question that we want to ask. So when are these? So you give it two bases, and when are these representations unitarily equivalent, and when are they inequivalent? And then now that's what. So now we can study it systematically. So let's understand the relation between the two representations. So here we already have a representation bar which is given by this. So I can just, to relate the two, I can just take this E sub bar, E under bar and E star under bar and substitute. So what we, to understand this, we can just say that, well, I know that phi bar x eta equal to 1 upon V naught times something. I'll do one calculation in detail. It's not very profound, but still, then you'll be able to do other things yourself. It's the same general idea. So I just write down this as e to the ik dot x times ek. So I substitute for ek, and I get here alpha k ek of eta times I get a bar k, right? plus beta k equals star eta times I will get here ak, right? AK here plus same thing here. So here I'm going to get here plus alpha star k k star eta, because I need here e bar star up here, so I just take the star of this equation plus I'll get here beta star k times k. So all I did was substitute for ek here, e under bar k here, and e under bar star here. That's all I did. But now we see that the coefficient of the a bar up here, right, has these two terms, e and e bar, e and e star, and the coefficient of a star also has this term. Therefore, if I pull together, something is wrong.
Start on that. Yeah.
Okay. So you get here ek. So the coefficient of ek up here has, I get here, if I pull out ek, I will have alpha k times ak, a bar k, plus beta star k times a. Okay. So I'm just rearranging the terms so that I can compare it with this formula up here. So I'll get here b naught k times e to the high k of x times alpha k e k of eta. So alpha k bar k alpha k e bar k times e plus beta star k times a direct k. Okay. Plus I'm going to get the Hermitian conjugate of this operator plus these other two terms that are left out here. So plus Hermitian conjugate of this operator. I'm just not writing out just to save space. But now we compare this operator phi bar in this particular way, and we see here that in fact this expansion that we did of this operator is really like the expansion we did of phi hat of k up here, except that, so this we want, if it is unitary equivalent, we would say that this is the same as v naught times summation k times e to the I x times this thing up here, which is just going to be ek times ak plus Hermitian conjugate. Now e to the ik dot x is a complete basis, and ek's are also complete basis up here. Therefore, the statement is that if these expansions are going to be equivalent to each other, then it better be true that ak up here is equal to alpha k under bar plus beta star k. So the statement is that, in fact, I got these two representations, and if in fact they are going to be literally equivalent, then in fact ak, it should be really, the ak in the first Hilbert space is a linear combination of the creation and annihilation operators. So the annihilation operator on the Fock space F is a linear combination of creation and annihilation operators on the second Hilbert space. Okay, so that's what we're seeing, that they're actually linear combinations. Yeah.
So you've equated phi and phi bar.
Why?
Yeah, because I mean.
So the real statement would be that. So I've been taking a shortcut here. I've equated phi with phi bar here. So the real statement is here that if I were to take this operator ak up here, and if I were to map it to the other Hilbert space, so the real statement would be that if I take AK, and but I want to operate on other Hilbert space. So I take U times psi, U minus 1. This object should be equal to this object. I'm just taking a shortcut up here too. So this should be equal to U minus 1. So the thing is that if they are both unitarily equivalent, then the statement is they are really operators on the same Hilbert space, right? Because I mean, I can just pull back. I can identify, and implicitly identifying it in this particular way. So you are completely right. So this object should be this. Really what I should do is to write down the abstract algebra, then introduce a representation mapping, and then do all these things. But this is the statement. So why is this happening? Well, it's just happening because of what happened here. We can just see here that this was supposed to be the analog of the positive frequency solutions, because this was the analog of e to the minus I omega t upon square root of 2k or 2 omega k if you like. This was the analog of that, so this is the positive frequency solution. And what we see here is that what we want to call it as a positive frequency solution in the bar representation is a linear combination of the positive frequency solution and the and the negative frequency solution. So basically the statement is that in a curved space-time, we do not have a canonical notion of positive frequency solutions in general, and in particular if it is time dependent, then what we mean by positive frequency solution at one instant of time acquires both positive and negative frequencies at the later instant of time. This is kind of the intuitive way to understand what is happening up here. But here what we did was to just choose two bases, and just because we choose them non-trivially related to each other, if I just put alpha k equal to 1 and beta k equal to 0, then of course the two bases are the same. If I don't do that, then the statement is, actually I could also put the normalization condition up here is really alpha k squared minus beta k squared equal to 1. That's a normalization condition. So I could also put alpha k to be a pure phase. If alpha k is just pure phase, okay, and beta k is 0, this condition is still satisfied, because if it's pure phase, its square is equal to 1. So if alpha k is pure phase, and beta k equal to 0, then the statement is that in that case, as you can see here, if beta k is 0 and this is pure phase, then A bar k is just related to AK by a pure phase. But the vacuum state is just selected by AK operating on vacuum equal to 0, so if I multiply it by pure phase, it doesn't make any difference. So the statement up here that we're seeing is that if in fact alpha k is pure phase, again this pure phase can depend on the k, but should not depend on time. And beta k is equal to 0. Well, beta k then will have to be equal to 0 because alpha k squared is equal to 1. So beta k will have to be 0 in that case. So then the statement is, what we find up here is that the annihilation operator AK is just equal to alpha k e to the I beta k times A bar k, right? Because this term is not there, so we just equal to that. And then we know that the vacuum state, the first vacuum state is defined by this equal to 0, the second vacuum state is defined by this equal to 0 for all k. But the two are just related to each other by phase factor, therefore of course the two vacuum states are the same. Of course everything is true up to phase factor. This defines the vacuum state only up to phase factor anyway. This is defined by. So the statement is that really, in this case, the statement is that the two representations are identical. In other words, U mapping up here is a trivial mapping. U mapping is identity mapping. Because the two vacui are the same, and therefore there is no the U mapping, or if you like, U mapping is a pure phase mapping, and pure phase mapping is the same as is a trivial mapping. There's nothing new about it. Vacuum state in one representation is the same as a vacuum state in one representation. One particle state will be the same as one particle state, etc. You look puzzled.
Yeah, I can imagine like phase interference effects, but if you only have one state that you're actually looking at, then that's probably not going to matter.
The phase factor is the thing that you're talking about?
So yeah, like I can imagine like, usually you don't want to throw away like the phase of like a state if you're going to compare it to like other states and do amplitudes, that kind of stuff. But because we only have one vacuum state,
Yeah.
that overall phase probably doesn't matter that much.
Yeah.
Right?
So the two things are in this case clear. So that's the first relation. And the second relation is we want to know what is happening in general. So we see here that the AK is linear combination of analysis. So in general, the vacuum state in the first Hilbert space is not the vacuum state in the other Hilbert space. Again, in answer to the question that Taro just asked, that Neil just asked, I'm again, this Hilbert, of course the two are not equal to each other because they live in the two different Hilbert spaces, but if they're unitarily equivalent, then when I say this is not equal to this, I just mean you, this vacuum. If I map by U on this vacuum, I do not get this thing. Right? I'm just dropping U's just to make life, the notation simpler on the board. All right. So the two are. So now, therefore, the statement up here is that, well, so what happens if this is not a pure phase? If in fact, this is some norm and this is some norm up here. Remember that this minus this is equal to 0. So in fact, there is no really bound on this on either of them, right? I mean, it's not that they're bounded by 1. Okay. So then the question is, what happens in that case? So let's just understand this. So we can just look at the inverse mapping also. It is very easy to check that this is the inverse mapping just using our normalization condition up here. The inverse mapping up here is going to be equal to, so what is Ek equal to? And Ek is equal to alpha k star E bar k plus minus beta k times E bar k star. So this is the inverse map of the map that we assumed. These are given E, what is E bar? Given E bar, what is E? So that, and you can just, in other words, you can just substitute and check that this is an identity, and you have to use this normalization condition critically up here. Or if you like, I got a 2 by 2 matrices, Ek and E star k, and this is just a, sorry, Ek and E star k you can think of as a column vector, and alpha and beta are just a 2 by 2 matrix, and so you just invert that 2 by 2 matrix, and you get that. So let me make sure that my signs are right, because I know my memory is not good at signs. Ek is equal to alpha star. Okay, so that's the inverse map then. And then as a result of that, we can also write down what is the relation between the inverse of this relation up here. And so you find here that A bar k, yeah. So similarly, we can write down here that A bar k, this operator is going to be equal to alpha k star, which I can just take it from here, times Ak minus beta k star times A dagger k. So this is, I mean, you do the same thing again in the inverted way, and you just find that this is a relation up here. But we also know that A bar k operating on vac bar on this state is equal to 0. So we would like to know what this state is. Again, I'm thinking of them as living in the same Hilbert space, so I'm dropping the U's, the unitary mapping. And therefore, Ak operating in this vacuum is equal to 0, so that this says that alpha k star times Ak minus beta k star times A dagger k operating on this vacuum is equal to 0. Recall that, in the first representation, the vacuum vac up here is just defined by Ak is equal to 0. So which means for all k, both these equations hold for all k. So it is clear that this vacuum state in general is not the same as this vacuum state in general in this, even though the two representations are equivalent. right? They're unitarily equivalent, but the physical meaning of the vacuum state is quite different in the two representations. And this is what we now want to understand much better. Okay, so if this is, so if in fact this state up here is not the vacuum, is not this vacuum state, if the barred vacuum state is not the same as the unbarred vacuum state, then I should be able to express this barred vacuum state in terms of the unbarred vacuum state up here and its excitations. I should be able to do that. And this equation is easy to solve. It's actually just a mode by mode, so there's no mixing of modes. So for each mode, we can just solve this equation. It's think of it's like an harmonic oscillator, because algebra dynamics is different, but here we're just looking at one. I mean, alpha case and beta case don't depend on time. A and A dagger don't depend on time, so dynamics has gone out completely, and we're just solving this on a Hilbert space of harmonic oscillator. So it's very easy to solve, and you find that the solution is just that the vacuum. And this is an exercise, a very simple exercise for the harmonic oscillator. You can just look for the state which actually does this, and we find that this is just equal to some normalization constant, which is finite. Well, which is the normalization constant times some e to the 1/2 summation over k times beta k star of 1 alpha k star times. So it is really the first vacuum operated by exponential of a quadratic combination of creation operators. If it had been, if I take a state psi, which is of the type, e to the some constant, so let's call it gamma k times dagger k operating on vacuum. This state is a coherent state. This state is going to be peaked at some point in the phase space, which is really given by this gamma. Gamma is a complex number, so it's q plus ip, and that gives me a complement. And this state is a coherent state that you must have studied in quantum mechanics, in harmonic oscillator. It's exponential, the creation operator operating in the vacuum with some coefficient, and that coefficient dictates where this state is peaked. So coherent states are the minimum uncertainty wave packets. They minimize the uncertainty both in Q and P, and they are sharply peaked at some point in the phase space, and that point is determined by this complex number gamma. Okay. But this is not like that. This is really two of them. These states are called the squeezed vacuum. That is to say, if I am going to look at my unbarred representation as being the fundamental representation, and I use a creation and annihilation operator as an unbarred representation to define P and Q, right? Because I got P and Q operators are linear combinations of creation and annihilation operators. So if in the unbarred representation, I'll get some P and Q. Then the statement is that this state up here is really squeezed. So it might be and that squeezing depends on this number, alpha and beta. So in other words, whereas the coherent states coherent states have the property that they are sharply peaked, they're like Gaussians, peaked around some classical point in the classical phase space, and the uncertainty the P and the uncertainty the Q is the same. If you make them to have same dimensions as is done in textbooks, right? You have this Q hat and P hat, thing that are used using the mass and the frequency of the harmonic oscillator, then the statement is the uncertainties are equally distributed. Whereas in this state, with respect to the P and Q operators that are defined by unbarred creation and annihilation operators, so you define A plus A dagger is equal to 2Q, if you like, and A minus A dagger is equal to divided by 2I is equal to P. If you do that, then we can look at the uncertainty relations, and this vacuum state will be peaked at 0. The unbarred vacuum is going to be peaked at a point Q equal to 0, P equal to 0, and the uncertainties are equally divided. Whereas this state, the barred vacuum here, is a state which is still expectation values of P and Q still will be 0, but the statement is that the uncertainties in the P might be squeezed, but then by the uncertainty principle, the uncertainty in the Q is actually longer, or the vice versa. Which of them will happen depends on this complex number. These are the squeeze stairs. And this happens for each mode. Yeah.
Why is it not capital A?
Oh, sorry, capital. All capital. Thank you. Thank you.
Is the upper special than beta? Why upper can't be 0?
Because of this relation, right? If alpha is 0, you cannot satisfy this relation.
Oh.
It's in the denominator, but you cannot satisfy this
Oh, yeah.
relation. So this transformation of creation and relation operators is called the Bogoliubov transformations. And the statement is that these alpha and beta are often called the Bogoliubov coefficients. Yeah, so that was a good question. Alpha cannot vanish because we have to satisfy. So the alpha and beta are not arbitrary, they have to satisfy this condition. Okay. So if you like, I can, yeah. I should just stop it. Okay. I was just going to say we can simplify this further by using this fact and by the fact that pure phase does not matter, but let's not. It's just algebra that you can do it, but there's no great conceptual insight you get by that. Technically, it's convenient to do that, but we don't get a great conceptual insight. All right. So now that we say that if it is unitarily equivalent, then all this is true. So, but when are the two representations unitarily equivalent? Now, if you had just single mode, if we had a single mode, or if only a finite number of modes, if we had only a finite number of modes, right? Then this sum up here is going on only a finite number of modes, and in fact, I displayed for you explicitly what the image of this I displayed for you this vacuum state explicitly here. If you like, so I displayed for you explicitly the unitary map displayed. If I know what the relation between the vacuum states is, then and I know the relation between the creation and annihilation operators, I know what the relation is between any state. Right? So I displayed for you this way. And if we only had a finite number of modes, then this is completely well defined because this is finite. This sum is all finite. So then the unitary map exists and is well defined. And this is basically the reflection of the Boyd-Nymann's theorem that I told you about. If you have finite number of degrees of freedom, then the representations of the canonical combination relations are always unitarily equivalent, and this is really a subcase of that canonical the subcase of two representations which are both representations of the canonical combination relations, and therefore they are equivalent, and we see explicitly what the equivalence is. The problem is if you have infinite number of degrees of freedom. If you have infinite number of degrees of freedom, this sum does not have to converge. You can keep going. And whether this converges or not, of course, A and A are just fixed operators. Their normalization is completely determined. So that all depends on this case up here. The key question is whether in fact these beta k's are going to die with that in the numerator sufficiently fast as you go out to large k's. If that happens, in other words, what is happening is that we have got mixing of creation and annihilation operators. If for large k's, this mixing becomes smaller and smaller. If beta k were 0, then there is no mixing at all. If this mixing becomes smaller and smaller, then you would expect this to converge. If the mixing is not smaller and does not become smaller and smaller, then you would expect that this would not converge, and therefore things are not unitarily equivalent. So now there is a necessary and sufficient condition, and namely, is this operator well defined? That is the necessary and sufficient condition for the unitary operator to exist up here. So we could do that, but that takes half an hour, so let me not do that. I'll just tell you a short, kind of physically plausible result. I will do we will derive a result which then sort of physically might suggest for you that this would be the necessary and sufficient condition, and in fact that is the case. Namely, let us ask, so let's suppose that if we have infinite number of degrees of freedom, or we had infinite number of degrees of freedom, so therefore the question is now, what happens in this case? So in that case, the question is whether that operator exists. So what we can do is the following. We can calculate the number of, either way, it doesn't matter, but I calculated one way, so let me just ask this question. We can ask how many particles there are in the bar vacuum. So I got this bar vacuum up here, and I can ask how many particles there are in the bar vacuum. These are the unbarred number of particles. So we are asking what is the expectation value of the number operator corresponding to the unbarred creation and annihilation operators in the bar vacuum. How many excitations of the original Fock representation F, how many excitations of the unbarred creation and annihilation operators there are in the bar vacuum? That is a question like that. So this is very simple because this is just equal to vacuum times this vacuum. Well, I can use this formula explicitly, or it's much easier to just use the number operator up here. You can do either way. You can either write this as this, and then the statement is that you would have to just take the number operator and commute it with this annihilation creation operators, or it's simpler just to write down the number operator up here, which is equal to the annihilation times the creation operator, the number operator up here, and then we can just write down it in terms of the bar creation annihilation operator. So this number operator is just given by AK dagger, AK, with the no bars here. So this is what we obtain. I'm just not doing anything. I'm just writing out the definition of the number operator, and therefore this is just equal to. Now I can expand out. I can write out AK. AK up there is equal to alpha K. Yeah. We can write down this as alpha K times A bar plus beta K star A dagger bar K. That is this I have to take a dagger of all of that times AK, which is alpha K times A bar K plus beta star K times A dagger. So instead of, and then I add the bar vacuum up here. Now the statement is that everything is barred, the vacuum is barred, the operators are barred, so I can evaluate this very easily. Let me not write down another step if you don't mind, and just simplify this dagger here. So if I simplify this dagger here, I will use another chalk. So I remove this goes away, this goes away, and I get star. So basically I just taken care of a dagger kills this dagger, A dagger is 1, and then I get here, A becomes dagger, and this becomes star up here. So now we just have to expand this out, and this is it's really trivial, because we know that annihilation operator, if it's bar annihilation operator operates on bar vacuum, I get 0. Therefore, it is obvious that this is not going to contribute. This term will not contribute in this expansion. And in this expansion, the dagger, bar dagger, operating on the bar vacuum on the left-hand side is also 0. So this is not going to contribute. So this doesn't contribute, this doesn't contribute. So we're just left with one term, and that term is just a dagger and then beta star. So the term that is left up here is just given by beta k squared times vacuum a bar k times a bar k dagger vacuum. Right? This is a vacuum times I'm going to get this, which is a, and then I'm going to vacuum times this, which is a dagger, and beta star beta comes out and get that. But this is just equal to 1, because this is just a dagger operator. This is a one particle state, this is a one particle state, so this is just equal to beta k squared. So the number of unbar particles in the bar vacuum is just given by beta k. This is exactly what you might have suspected, because the mixing between creation and annihilation operator is happening because of beta k. If beta k were equal to 0, then alpha squared is equal to 1, alpha is pure phase, and then the two vacui are the same. So the mixing is just happening there, and you would have hoped that there is some simple relation between the number of particles, number of unbarred particles in the bar vacuum, and beta k. By the way, if you had calculated the other way around, the number of, it's a good exercise to do, the number of bar particles in the unbarred vacuum, you again obtain beta k squared, exactly the same answer. So it's nothing new up here. So therefore, the statement is that if we have got all the particles, I mean if we have all the Bohrs, therefore the total number n of particles, this distributional summation of k times so this is the bar vacuum, these are the unbarred particles, how many are there? So we just find that, and that of course is just going to be equal to summation over k times beta k squared. Okay. And so therefore that's the answer that we find is equal to, and so the question is this finite? So it's sort of intuitively obvious if this is infinite, then of course the two representations would not be mutually equivalent. And again, intuitively you might expect that if this number is finite, then that means that this is a state with a finite number of excitations or particles with respect to the unbarred vacuum, and therefore it's in the Hilbert space, everything will be perfectly fine. And this expectation is correct. I'm not proving it for you, but this expectation is correct. So the statement is a necessary and sufficient condition for representations to be unitary equivalent is that the beta k, the two bases are related such that the beta k is finite. So again, I've not proved that for you, but it is plausible. What we have proved is that if you calculate the number of, say, the unbarred particles, the bar vacuum, the total number of particles, you get this number up here. If this number is finite, then it's plausible that that means that this state does exist in the unbarred vacuum, in an unbarred Fock space, because it has a finite number of particles, so therefore it should exist, as you would think, and therefore its norm should be finite, and then and the statement I'm making is that this final remark is really true, that this is a necessary and sufficient condition for the operator U to exist, that is to say this nk to be finite, not nk, I should say, this is n only, this n to be finite, there's no k here because sum load k, so this n needs to be finite. If I had not sum load n, then this would be nk, but now there's summation of k up here. So this n had to be finite, and the statement is that that is the case. Okay, any questions about this? Yeah.
What's the consequence of what's the physical consequence of having two vector which are unitary and equivalent?
Right. So that means that the represent. So this is the thing that we're now going to discuss. So if you look at the basis of the representations, if I look at this basis, there is some set, and I got bases like that. So this is the space of either basis or state or vacuum, or the vacuum, whatever you want to call it. I mean, Fock representations up here. So it's some state, and that state is divided into sectors up here. So these, any one of them, I'm dividing into parts so that any one of these boxes up here are unitarily equivalent. So if they are unitarily equivalent, then the statement is that then they're physically, I mean, I can translate results obtained in one representation to results in another representation. I can live with them, there's no problem. And the example that all this shows here is clearly that if beta k's were to die sufficiently fast, right, with respect to k, then the statement is that they would be unitarily equivalent. That is, the mixing of the creation and annihilation operator dies at large k, then there is no problem. At the small k, there would never have a problem. The reason is because k equal to 0. It's not, it's not a very, I mean, we don't go, k doesn't go to from minus infinity to infinity. This k up here, it just goes from 0 to infinity, so there's no problem there. So we're good. So the problem up here is that, but of course you may have some another unitarily equivalent representations. So representations here are unitarily equivalent, but they are not equivalent with respect to this. So if I calculate the number of particles in this representation, in the vacuum of this representation, I'll get finite answer. But if I calculate the number of particles in this representation with respect to vacuum in this representation, I'll get infinite answer. So if this happens, if they are unitarily equivalent, then the statement is that I really cannot translate the results from one Hilbert space to another Hilbert space. There's really quite a, it represents different physics. Now I should just add a small caveat that there is a notion of physical equivalence which is slightly weaker than unitarily equivalence. I'm just telling you in case you look at the literature and find that. But this is something that is done by more rigorous people, and for practical purposes. If it's unitarily equivalent, we're going to people just say that that means that the physics here is really completely different from physics here. So we have to make a choice. We're getting infinity many of these representations, and we have to make a choice. It's not something that is God given. We really have to make a choice up here. Now you might say, wait a minute, but what happened in Minkowski space? Why is it that we had a unique representation? This representation was a Fock representation, and as I was telling you before, it is selected by the Poincare invariance. So it is selected. So in Minkowski space there is a, but in Minkowski space you might say, I don't care about Poincare invariance. I might violate it slightly. For example, I keep for example the space translation. This is something that people do sometimes. For this something like this Hojava-Lipschitz gravity that you might have some spatially everything is nice, but in fact in terms of time it is not Hojava-Lipschitz gravity. It is just quantum field theory in curved space-times in the spirit of Hojava-Lipschitz gravity, that I just want to keep the Euclidean invariance, but I don't necessarily need to have a boost or the time translation invariance. In that case, you can choose other E case, and in that case there is an infinity many representations of the commutation relations, even in Minkowski space. Right? Because I can just do this. I can, to begin with EKs that way I got up here, these in standard Minkowski space are just e to the I kt or e to the I omega t upon 2k. But I can just define E bar k by the formula that we had before, mixing of the creation and annihilation operators. And then with alpha k and beta k are non-trivial. And then I'll find the representation in which there is Euclidean invariance, but there is no Poincare invariance. So I can find such representations even in Minkowski space. And that physics is unitarily inequivalent to the Poincare invariant physics that we talk about. Okay. So this is what is happening. So the question is then, what do we do in general? Now in cosmological space-times, there is a reasonably natural choice that people make in cosmological space. And we're only talking about cosmological spacetimes here anyway. So in quantum field theory in cosmological spacetimes, we can make a natural choice. I mean, we don't have a Poincare group, we don't have time translation symmetry, so there's going to be Poincare, there's going to be mixing of positive and negative frequency as we go, as we time evolve. That is going to happen anyway. But we can select a class of representations which are unitarily equivalent, right? So that as time goes on, only a finite number of particles or finite number of excitations is produced, not infinite number, and we can compare. So physically, what does it mean? You see, notion of particles as we see in the curved space-time has no fundamental basis, fundamental meaning up here, because it depends on the choice of the vacuum, and even if you choose unitarily equivalent representations, there are different ones, and the vacuum state here is not the same as vacuum state here. So the number of particles, as we just saw, does not have any invariant meaning. The number of particles in this representation, the number of barred particles in this in the barred vacuum is 0, but the number of unbarred particles in this barred vacuum is not 0, it is given by that. So number of particles excitations doesn't have fundamental meaning. This is kind of goes against the philosophy that people use in particle physics very much, because there particles are the fundamental things, and, but it's true in quantum fields in curved space-times. So why is this happening? Well, physically it is happening because I got a time-dependent geometry, and therefore this time-dependent geometry can pump in, can excite the vacuum state as time goes on, and you will get more and more so more and more excitation. In other words, there can be transference of energy from the background. This is quantum field theory, the fixed background. So we're assuming that the back reaction is negligible, and in a fixed background, the statement is that you've got a reservoir of energy, and the quantum field can suck energy from that and create particles. So in particular, a quantum stress and intensity in the quantum in the stress and intensity at a given instant of time in a particular representation, in a particular state, can be 0, but at another instant of time it will be non-zero because one has actually sucked energy from the field. This is not surprising because we've already seen this in classical theory, right? If you have got a classical field propagating in a time-dependent background, there is no time-like killing vector field, and therefore it is a fact that there is no conserved energy. Energy of the field is not conserved. So here we see it in the quantum context. Now, in cosmological spacetimes, what one does often is to use demand regularity, ultraviolet regularity. And for historical reasons, one uses the term adiabatic regularity, but there's nothing necessarily adiabatic about it, but the term has stuck. One demands this. So what does it mean? It means that what we want is the following. We got this basis vectors Ek. And if I go to this chi k, which is given by A times Ek, then we saw that this chi k is up here satisfies some different equation, which is very simple. Chi double program plus A squared times K squared upon A squared plus the minus the scalar curvature upon 6 times chi is equal to 0. So we saw already that if K is much larger than K upon A, K physical, if this is much larger than the scalar curvature, so if you are modes with very high energy, I mean very high wave number, I should call it high energy, ultraviolet modes, so high wave number up here, then this term is negligible and this becomes like a Minkowski spacetime, right? To the very leading order is just Minkowski spacetime. And then the statement is that if it is Minkowski spacetime, then we know that the modes EKs should behave like this, e to the I omega minus I omega t upon square root of 2k. So we know that. So the statement is that we just want to ask that A of eta times Ek in the large scale limit should behave, should approach e to the ik eta e to minus ik eta, that's equal to 2k in appropriate manner. So we don't want it to approach just any old manner, but they should be approached in some controlled manner. And all the technical details are of what is meant by appropriate manner. So this appropriate manner is chosen so that you can regularize products of field operators, and for us most interesting is the stationary tensor operator. In Minkowski space-time, the stationary tensor operator can be regularized by just normal ordering. Here, normal ordering does not work. You have to subtract out some other part, and what you have to subtract out to regularize the stationary tensor up here will depend on what A is. And so what we want to do is we want this to approach e to the minus ik eta upon square root of 2k, but in such a way that we can regularize the stationary tensor and obtain an operator which is acceptable. So which, for example, has a property that is divergence equal to 0. It satisfies various conditions we want it to satisfy. And the statement is that this can be done, and states which satisfy this condition are said to be adiabatic to order 4. It is order, in other words, the appropriate manner is really how fast the states approach, the basis functions approach the Minkowski basis function up here, and the rate of approach is called the adiabatic order. And this order 4, in the sense, because the stationary tensor, if you like, is a dimension 4 operator, that is why it is of order 4. So that is to say, we say that the corrections to e to the minus ik eta upon square root of 2k, in this case involve the scale factor, they involve the first derivative of the scale factor, second derivative of the scale factor, and the third derivative. So it involves 4 terms, the behavior of these objects. In Minkowski space, all these terms are trivial because A is 1, so all of them are 0. But in the expression of this Ek, you will find the Ek which are regular to order 4. You will find not only this term, but corrections to this term, which involve A prime, A double prime, and A triple prime. And this is something that we can read in some detail. It's a very complicated subject if you want to understand from books. You should understand from books. But there's a very succinct summary of all, both the conceptual things and what you'll actually use in practice, right? Both of those things. There's a succinct summary in the paper, which is so this succinct summary up here is a paper by Aguillo and Nelson and me, and it is, look at this section, don't have to read anything else. This section is self-contained, 6a, and it's PRD 80. It's also on archives, 87 043 507 2013. This is relatively recent because historically it was obtained in some way which is not the most useful logically, and this actually explains this whole bit rather important but technical result, and it explains the conceptual underpinnings and what you have to do in practice to ensure that your basis is of this order. If I had done that, then the statement is that this regularity then will select for me a class of unitary equivalent representation. So this is selected by adiabatic regularity. In any cosmological spacetime, you can do that. You can select unitary equivalent representations by this adiabatic regularity condition, and then that's what we use. Because those are the ones which have a nice ultraviolet behavior. Okay. So this is really the main point of the general quantum field theory in curved spacetimes. Next time we're going to use all these things to see how connections with observations are made. But for that, we have to talk about inflation. And therefore, as a precursor to the inflation, I just want to make a remark about de Sitter spacetime. Because as we'll see, because inflation is like nearly de Sitter expansion, nearly exponential expansion up here. As we saw when we did the very first part of this very early universe, we saw that if you've got a scalar field and if it's rolling very slowly, then the kinetic energy is zero, is negligible compared to the potential energy, and therefore the pressure is negative, and we got P equal to minus rho, close to that. So equation of state is really that of a perfect fluid with P equal to minus rho, and when that happens, we saw that the Raychaudhuri equation and the Friedman equation tell us that there is an exponential expansion. So here in inflation, we don't have exactly de Sitter spacetime. We have near de Sitter spacetime, as we will see, but an idealized case is de Sitter spacetime, and so what we want to, therefore I would like to tell you what happens up here. So the de Sitter spacetime, that is a cosmological spacetime, if you like. You can think of it as a cosmological spacetime, in which I got scale factor, and then again, it is exactly at this time, where this A squared, if you like, is just given by 1 upon what is called Hubble parameter squared times eta squared, and the Hubble parameter is just given by lambda by 3, the cosmological constant divided by 3 up here. So we got a de Sitter spacetime, so we got a positive cosmological constant lambda, and then the statement is that this object up here is just given by 1 upon h naught squared. So 1 upon h naught squared will be equal to 1 upon lambda. So this is just given by 1 upon h naught squared times E. You can see here that it's not trivial to take the Minkowski limit. Those who are interested, please come to the office hour. I'll tell you about the Minkowski limit. The reason is because if I take lambda goes to 0, that means h naught goes to 0, then this just blows up. This metric doesn't make any sense. But there is a way to take Minkowski limit properly, and but it's not using eta x coordinate. It is here using proper time coordinate. Then you can take the Minkowski limit very well. So we got this is the Minkowski. This is the de Sitter metric up here, and this is like Minkowski metric in which it has 10-dimensional Poincare group, a 10-dimensional isometric group, which is de Sitter group. Poincare group. Poincare group is from Minkowski space. Here we have got again 10-dimensional isometry group. So we can again, we have got extra structure. We have this extra structure up here that we can use. Namely this isometry group that we have, and that's what we use. And then the statement is that this selects for us a basis with this extra structure, where we're requiring that the 2-point function be de Sitter invariant. So if you ask that the 2-point function be de Sitter invariant, then the statement is that you are going to get you are going to select particular, this is again 4th order regularity. So we ask for the 4th order regularity. So again, we have somewhere here in this case, and among them we ask in addition that way I got de Sitter invariance. And just as in Minkowski space we select out a unique representation, here also we select out a unique representation. There's a subtle technicality associated with the k equal to 0 mode, which is kind of because of the infrared problem that are I'm just ignoring that subtlety. That subtlety is there both in Minkowski spacetime and de Sitter spacetime. It doesn't cause any physical issues, physical problems, so I'm just ignoring that infrared subtlety. And that's also why I put everything in a box. Right? So we don't approach k in a continuous manner, but there's a issue about k equal to 0 itself. Okay. So this is a 2-point function, de Sitter invariant. And what are these basis vectors then? The basis vectors in this case, for the de Sitter case, are just given by ek of eta in the de Sitter case, and this is just given a minus h naught times eta. We can write down them explicitly. Just like what we did in Minkowski space, we can write down the basis vector explicitly, which are compatible with the Poincare invariance. We can write down them explicitly here, minus eta pi upon 4. In the usual convention, eta is always negative. Eta equal to 0 is sort of infinity. So minus. Okay, here you got here Hankel function of first kind of order 3/2 of eta. And if you expand it out, then this is just equal to h naught eta. Maybe it's exactly equal to even, I'm not sure. It could be, I think it's probably exactly equal to that. It's just equal to h naught eta upon square root of 2k times 1 minus pi upon k. So what I'm trying to say is that there is actually, wait a couple of minutes. So there is actually an explicit expression that replaces this expression up here. As I told you before, we cannot just bluntly take the limit h naught goes to 0 or lambda goes to 0 in this, because everything will look like it just sort of doesn't make any sense. And the point is that you have to express it not in the eta coordinates, but in the proper time coordinate. In the proper time coordinate, take the limit, and then everything is okay. Then h naught times eta is replaced by just goes to 1, and you'll be able to get a good limit of this completely, and that limit is exactly this limit. So if you do it properly, you will get the same as the Minkowski metric limit that we're having. So we do have symmetry requirements, do select a unique representation, and therefore we get a vacuum state, which is annihilated by this, and this is the de Sitter vacuum, and this vacuum was first discussed by Timothy Bunch and Paul Davies, and it's called the Bunch-Davies vacuum. So the Bunch-Davies vacuum really refers to de Sitter space-time, and next time we're going to see how this Bunch-Davies vacuum is used to do in inflation in order to sort of get all the predictions. So again, to summarize, so far we got 3 parts. First was just introduction, telling you about the background dynamics. The second was about cosmological perturbation. The third was about quantum field theory in cosmological spacetime. We're now going to put all of them together to talk about an inflationary scenario. I'm going to tell you how one calculates the power spectrum in the C and B, and that power spectrum is calculated from first principles using all these things that were introduced, and then we of course compare it to experiment and what happens. So that's what we will do next time.